The next technique is called squeeze or sandwich theorem, which is similar to the squeeze or sandwich theorem from Calculus 1, except it's for sequences. If you have a sequence B sub n that is sandwiched or squeezed in between two other sequences, A sub n and C sub n, for all values of n, and also the limit of the nth term of the upper and lower sequence converge to some limit L, then the sequence that is sandwiched in between them will also converge to limit L. So here we have a picture of this. You can see that the sequence Bn, which is in red, is always in between the yellow sequence An and the blue sequence Cn. And as n becomes large, they all converge to the same limit L. In the next example, does the sequence converge or diverge? So here we have the sequence 1 plus sine of 2n over square root of 1 plus n. When we take the limit as n becomes large, sine of infinity does not exist. We have does not exist divided by infinity. But we also know that sine theta is bounded in between minus 1 and 1. So when you divide by a very large number, you should get 0. So here we can use the squeeze theorem. Since sine of 2n will be in between minus 1 and 1, then we can say that 1 plus sine 2n will be in between 0 and 2. And if we divide the inequality by square root of 1 plus n, then our sequence will be sandwiched in between 0 and 2 over square root 1 plus n. We can also see that the limit as n becomes large of 0 is equal to 0, and also the limit as n becomes large of 2 over square root 1 plus n is also equal to 0. So by squeeze theorem, the sequence will converge to 0. Next, we have a note on factorials. For n a positive integer, this notation n with the exclamation mark is n factorial. So that will be equal to 1 times 2 times 3 ... until you get to n. And the special case 0 factorial is just defined to be 1. So for example, 1 factorial is 1, 2 factorial is 1 times 2, which is 2, 3 factorial is 1 times 2 times 3, which is 6, 4 factorial is 1 times 2 times 3 times 4, which is 24, and 5 factorial is 1 times 2 times 3 times 4 times 5, which is 120. In the next example, we have sequence 3 to the n over n factorial. So here on the side, we can take the limit as n becomes large, and we get infinity over infinity, but we can't use L'Hopital's rule with factorials because they're not continuous. So instead, we'll use squeeze theorem. So on the bottom, we have n factorial, and on the top, we have 3 to the n. Here I have separated in green 3 over 4 times 3 over 5 times 3 over 6 until we get to 3 over n minus 1. That section in green will always be less than 1. Here in blue, that portion, 9 over 2 times 3 over n, will always be larger than or equal to an. So now we've squeezed the sequence an in between 0 and 9 over 2 times 3 over n. And since the upper and lower sequences both converge to limit 0, by squeeze theorem, this sequence also converges to 0. The next technique is for alternating sequences. So these are sequences that are alternating in between negative and positive values. We can just consider the absolute value of them. And if the absolute value of the sequence converges to 0, then the alternating sequence will also converge to 0. In the next example, we have minus 1 to the power n over n. We see that this is an alternating sequence, so we can consider the absolute value of it. For the absolute value of the nth term, we can just eliminate the term that makes it alternating, the minus 1 to the n. So we have 1 over n. And since the limit of the nth term is equal to 0 for the absolute value of the sequence, the alternating sequence also converges to 0. Also note that for alternating sequences, if the limit of the absolute value of the nth term is not equal to 0, then the sequence will diverge, since the sequence will keep bouncing back between positive and negative values that are not 0. So in the next example, we have an alternating sequence. So we can consider its absolute value. So we take the limit as n becomes large of n over n plus 3 root n, which will be infinity over infinity. Here I will circle out the highest power terms. They have the same degree, so the limit will be the ratio of the coefficients. So here we have an alternating sequence, and the limit is 1, which is not equal to 0. So the sequence diverges. The following problem is about the Fibonacci sequence. The Fibonacci numbers appear often in nature. For example, the number of petals on these flowers are the Fibonacci numbers 5 and 8. The leaf arrangement of this succulent plant has 13 clockwise spirals shown in yellow and 8 counterclockwise spirals shown in red. This yellow chamomile flower has 21 clockwise spirals shown in blue and 13 counterclockwise spirals shown in green, which are also consecutive Fibonacci numbers. You can also find these numbers on the outer spirals of a pine cone, pineapple, or even the number of fingers on your hand. The Fibonacci sequence is defined recursively. The first term is 1. The second term is also 1. For n greater than or equal to 3, fn is equal to fn minus 1 plus fn minus 2. So in this way, a term is the sum of the two previous terms. Part A, write the first 10 terms of the sequence. And Part B, show that the value of this limit is equal to the golden ratio phi. So for Part A, we want to write the first 10 terms of the sequence. So the first two terms are given, 1 and 1, and the next terms are defined recursively as the sum of the two previous terms. So the first two terms are 1 and 1, and the next term is 2, since 1 plus 1 is 2, and the next term is 3, since 2 plus 1 is 3. After we have 5, since 3 plus 2 is 5. If we add 3 and 5, we'll get 8. And similarly for the other terms, 13, 21, 34, and 55. For the second part of the problem, we want to show that the limit as n becomes large of the ratio of successive terms in the Fibonacci sequence will converge to a limit L, and that number will be the golden ratio. So first we'll rewrite fn using the recursive definition. So L is equal to the limit as n becomes large of fn minus 1 plus fn minus 2 over fn minus 1. Then we can divide the two terms in the top by fn minus 1 in the denominator. So fn minus 1 divided by fn minus 1 will be equal to 1, plus fn minus 2 divided by fn minus 1. Next I will rewrite this second term, fn minus 2 over fn minus 1, as the reciprocal, so to power minus 1, of the ratio of successive terms, fn minus 1 over fn minus 2. So here we replaced fn minus 1 over fn minus 2 with the ratio fn over fn minus 1. When we take the limit as n becomes large, the limit of the ratio of successive terms will go to L. Next we'll take the limit term by term. So we have the limit as n becomes large of 1 plus the limit as n becomes large of the reciprocal of the ratio. Since the limit as n becomes large of the ratio is equal to L, the limit of the reciprocal of the ratio will go to L to the minus 1. So the limit L we are looking for is equal to 1 plus 1 over L. To solve this equation, we can clear the fractions by multiplying both sides by L. If we distribute the L, we will have a quadratic equation to solve. So we have L squared minus L minus 1 is equal to 0, and this we can solve by the quadratic formula. Here if we plug in A, B, and C into the quadratic formula, we have that L is equal to 1 plus or minus the square root of 1 plus 4 over 2, and the positive solution is phi, which is known as the golden ratio. In addition to appearing in nature, the golden ratio and the Fibonacci sequence are also used in computer algorithms, music, art, and architecture.